Okay, so today we start to study asymptotic space the hyperbolic plane. So first, what is hyperbolic plane or Lobachevsky plane? Lobachevsky plane is a plane where all the axioms of Euclidean geometry are valid, but the axiom, the fifth postulate of parallel lines is not. So in this case, if you have a line and we have a point outside of this line, then there exists more than one line which do not intersect the first line. So line 1, there are at least two lines going through this point P, so that they have no points in common with the initial line. With the line 1. No, in this case, any other line which goes between lines 1 and 2 and 3 is also parallel in the sense that it doesn't have common points with the line 1. So here we can say find the limit positions. So we rotate this line and then consider the last line which does not intersect, and all line which is inclined more do intersect line 1. So these are two lines. All the lines between them do not intersect the line 1 and are sort of parallel. This angle alpha is called length of parallelity. It depends on the distance from the point P to the line 1. It's some universal function which was found explicitly from the very beginning of the science by Lobachevsky. Yeah, so the story, I think you know the story that the attempts to prove the fifth postulate from other postulates started very early, and it was especially successful in sense how it was proved. It was proved by contradiction. The attempt was to prove by contradiction, assume that there exists several, more than one line, so there exist infinitely many lines, and especially successful in this proof. I mean, the people tried to go farther and farther in the way of implications of this new axiom, which was opposite to fifth postulate. It was done in 18th century by some Jesuit mathematicians, Seike, Sakeri. They already were close to build the whole new geometric system of geometry, and they never found this desired contradiction. And then the idea came to independently Lobachevsky, Boyer, and Gauss that there will be never found a contradiction. So, and this event is thought to be the beginning of non-Euclidean geometry. No, however, it was not exactly the true beginning, because if the contradiction was not found, this doesn't mean that it is not. So maybe the people did not try hard enough. So the final nail in this construction was made later by Klein and Poincaré, who proved the great theorem, result that if that this non-Euclidean geometry has no contradictions if and only if the Euclidean geometry doesn't have contradiction. Yes, so it is I would say, equi-consistent, these two theories, and moreover, the non-Euclidean geometry is some small special part of Euclidean geometry, and Euclidean geometry is a small special part of non-Euclidean geometry. So it is a property of large or infinite systems that the system contains in itself its own isomorphic images, yes, which we know from other examples. And so, how they did it? They produced this subsystem of Euclidean geometry, which is the new geometry. So I will use the Poincaré model. So it is a model of this geometry. Namely, it is a true model. So some objects of Euclidean geometry are called, say, non-Euclidean lines. Some are called non-Euclidean planes, and the new relations between them are introduced, which are images of the old relations. So, in the Poincaré model, non-Euclidean plane is the interior of unit disk. Model Z is less than 1. Model of non-Euclidean plane. You know, the name non-Euclidean is a little ambiguous because one astronomer wrote a paper called Use of Non-Euclidean Geometry in the Problems of Astronomy. And since that, this astronomer was called non-Euclid. Yeah. Yeah. So now, what is the line here? If this is the plane, the lines are the arcs of a circle which form right angle with this circle model Z is 1. So this is 90 degrees here and here. So these are, no, in particular, diameter. Every diameter is what is called a non-Euclidean line. So this is non-Euclidean line. Now, we want to define what are the motions or isometries here. Yes? So isometry are the conformal maps of this disk onto itself. Yeah? So these are transformations of this disk into itself, which play the role of isometries. At least they transform all the such curves, all such arcs which are orthogonal to the absolute. This is called absolute. They are transformed in arcs of the same sort. Now, what is the distance? What function is the distance? No, it is less obvious what is the distance here, but there is, it is better to introduce Riemannian metric on this disk, which is invariant under these conformal transformations. And this Riemannian metric is ds equals dx divided by 1 minus modulo x squared. No, let me, ds dx, the length of small segment here, ds is dx is the Euclidean length divided by 1 minus modulo x squared. So this means that as we go along, say, diameter, then the x Euclidean distance between the center and the absolute is 1, and non-Euclidean we have to integrate this, but this integral is diverging if you go along the diameter. Now, if you go along this arc of the curve between 2 points here, for any 2 points we can construct a non-Euclidean line which goes through these points, and then you have to integrate this. No, it is interesting integration problem. And the distance, non-Euclidean distance, d, between 2 points z1 and z2 equals 1/2 logarithm of 1 plus a, 1 minus a, where a equals modulo z1 minus z2, z1, z2 bar minus 1. Yeah, so this is a little bit tricky way to, so z1 and z2 are two complex points in this disk. To make it possible to work with these formulas, we have to write them in polar coordinates in the real form. So let us introduce polar coordinates. It is rho, it is phi. Yeah. So x equals rho phi in the polar coordinates, and then the formulas will be even worse. x1, x2. So xi, rho I, phi I, equals 1/2 logarithm 1 plus a, 1 minus a, where a squared equals 1 minus 8 divided by 2 minus epsilon square t plus 1 over t square plus epsilon square s plus 1 over s square. So what is s square equals e to the power rho 1 plus rho 2. T square equals e to the power rho 1 minus rho 2. And epsilon square equals 1 minus cosine phi 1 minus phi 2. So we have this formula, not very transparent, but we need this all to study the asymptotic geometry. This means that we have to shrink all the distances and look how it happens. So we are interested to see what happens if rho 1 and rho 2 are very large. And so this needs some asymptotic analysis, which I will skip for a while. So let us write rho I equals n times Ri. So and about the angles, phi 1 minus phi 2 equals e minus n phi capital. So why such exponential thing appears? It is because of the property of geodesics in the hyperbolic plane. So if you have two geodesics which start at some angle, say alpha, yes, start from one point and form angle alpha at this point. Then it turned out that the distance between these geodesics, we go the same distance along each of them, grows exponentially. Yeah? So if alpha is a very small angle, then this distance anyway grows exponentially. And so therefore to have 2 points close to one another far enough, two geodesics, if they have to be close to one another at some considerable distance, we have to establish the angle so small that this angle will beat this exponential growth. So this angle should be exponentially small. So if this distance is of the order n, and this is, say, of the order 1, for example, then this angle is of order e to minus n. Yeah? So we have this substitution, and then after we substituted here and look what happens if n is large, we have the following simple asymptotic formula. One over n t between x1, x2 equals maximum of the following two: R1 minus R2, R1 plus R2, minus 2, 5, plus O of 1 over n. So the main term here is this. If rho is n r, or let me d of x1 x2 equals maximum of moduli n, let me write rho 1 minus rho 2, rho 1 plus rho 2 minus 2 and 5, plus O of 1. Now we can multiply by n and have this. Yeah. Now let us see what does it mean. If there is a point O, the origin, and we have two geodesics, 2 points which lie on the same ray going through point O, say x1 and x2, then the distance between x1 and x2 is given by rho 1 minus rho 2, absolute value. But if they are at considerable angle between one another, then you have so in this case the angle is E minus phi, so phi equals minus 1 over n logarithm angle phi1 minus phi2 and 1 over n capital. And you see that when is larger, this becomes close to 0. So we have here that this term is larger, rho 1 plus rho 2. So what does it mean? This means that geodesic which going from this point to this, it goes almost returns to the origin and then goes this way. Yeah. So this is other situation. Okay, and now what is, we have to study this formula. In fact, this simple formula, it is all what we need to go on. We have to study, so we have rho is from 0 to infinity. It is the non-Euclidean distance from the center O to our points, x1 and x2. And they form angle which is given by, better parameterized by this. And we will study this formula. It turns out that this formula is hiding a lot of interesting things inside. So, having this in mind, I need some preparation which pertains to the non-standard analysis proper, which I'm going to do today. So now I will consider the following thing. It is called decomposition of non-standard numbers. Suppose we have a non-standard universe, and in particular we have non-standard real line. So this non-standard real line, what can we do with this? Let me explain. It is algebraically speaking a model over standard real numbers. So we can multiply every non-standard number by any standard numbers. Yes. So and we have all the properties of the model of any of the model over real the field of real numbers. Yes. So. Over R. So first of all, it is a linear space over R, and then it has some algebraic properties. So say A plus B x equal AX plus BX, CA or AB x equals A times bx. So here A, B are in R, x in star. Yeah? And A x plus y equal AX plus AY. A xy equals ax times y. These are the properties of a model over the field R. So my goal is to define something like basis in this model, yes, so that more or less every element of star R is decomposed into the sum of these elements of this basis with coefficients in real numbers. So this is a non-standard thing, but now I wanted to consider as a standard, so this means that it inflates greatly because, say, the cardinality of star R can be very large, and so we have to use some set theoretical technique to work with it. Yeah. No, this construction should require some, not some, but many choices, which choices, so I have a set, I have to choose one representative of this set. Yeah? So we have to use the axiom of choice, and we can somehow unify all these choices in the following way. So let me give a definition. A set, say A, with a linear order, this, so any two elements can be compared to one another, is called well ordered by this relation if the following is true for any set B in A, there exists a minimal element, say B in B. Minimal with respect to this element. So all elements of the set B are more than B. Let me. So B is the minimal element, not only the lower bound, but truly minimal element. No example, the set of natural number n is well ordered. Any subset of n has minimal element. Yes. The set of real numbers is not well ordered. So the set of positive number has no minimal element. Yeah? And there exists a great theorem, Shnirelman. Any set can be well ordered. No, I proved this theorem in my course of set theory, and more or less all the course was aimed to prove this theory. So we have to use this theory. And now let us use the following thing. Let us take the set star R, the set of all real, non-standard real numbers, is well ordered. By a new relation. Let me denote this relation this way, because there exists the usual relation more or less in star R, which is not well ordered, but we introduce a new relation. No, this theorem cannot be proved constructively, because if we have a set which is infinite, then if it doesn't have well ordering, then we hardly can constructively describe the well ordering which exists by the Zermelo axiom. But if you believe the set theory, then you have to believe the Zermelo axiom. Okay, and now I start my description how what is the composition of a non-standard number. Suppose we have yes. So we write x, if x, y in star r, we consider positive elements, star r plus. We write that x is equivalent to y if x divided by y less than some k, and y divided by x less than some k for some standard real k. The definition. So we have somehow a partition of non-standard reals into equivalence classes. Denote lambda is by definition star r plus factorized by this equivalence relation. So these are classes of more or less comparable in standard sense non-standard numbers. Yeah. So lambda, and elements of this lambda are called are denoted small lambda. Yeah. Now in this set lambda, we have also an order. No, just natural no order. So if we take two classes, lambda 1 and lambda 2, we can say if you take some representative of lambda 1, lambda 2 in lambda, so these are two classes of non-standard numbers which are here. All the elements here are mutually comparable in this sense, here also, but they are non-comparable. So we have, say, x1 in lambda 1, x2 in lambda 2, and we write lambda 1 less than lambda 2 if x1 less than x2. This does not depend on particular x1 and x2. So we can take any of them. So now I start yes. So, and we also define if x in star r, we define lambda of x is the unique lambda such that x element of lambda of x. Yeah. So it is the class where this element gets in our partition of set star r into these sets of comparables. And now let us start our process. Let us yes. Let's take x in star r, and we define, say x0 equals x. Lambda 0 equals lambda of x0. C0, one moment. One thing is absent. So we have lambda is a subset of star R, yeah, for any lambda in lambda. The following, lambda is a subset of star R. So if it is a subset of star R, so we can find the minimal element, A lambda is the minimal element of lambda with respect to this U relation. And now we take x in star R. We write x0 equals x. Lambda 0 equals lambda of x0. C0 is a standard part of x0 divided by a lambda 0. And also one more, s0 equals 0. Okay, let's make one more step. X1 equals X0 minus C0 A lambda 0. Lambda 1 equals lambda of X1. C1, it is a standard part of X1 divided by A lambda 1. And S1 equals C0 A lambda 0. So what essentially we did, we somehow found sort of the main part of our element. First, we found in which subset of our partition it is. In subset lambda 0, this number x. It's already defined. Now we found how it compares with this number a lambda 0, which is in this subset. This is a bounded number, so it has a standard part which is neither 0 nor infinity. Then the S0 is 0, it is beginning of one more sum. Now we take X0 and subtract this part. This is the main part. After this, this element is already in, if you take X0 minus C0 A lambda 0 divided by A lambda 0, yes? Standard part of this equal standard part of X0 divided by A lambda 0 minus C0. But what is C0? C0 is standard part X0 divided by A lambda 0 equals standard part of X0 divided by A lambda 0 minus standard part of X0 A lambda 0. So what happens here? This is a non-standard number, finite non-standard. We subtracted standard. This is a standard part of the same number. The result is infinitesimal number. Yes. So standard part of this is 0. So this means that this number x1, yes please.
How do you find x0 minus c0 a lambda naught divided by a lambda naught? Is it a lambda naught or a lambda 1?
What?
The first one is standard part.
This?
Below this one.
Next, x0 a lambda 0 minus c0 a lambda 0 divided by a lambda 0, this is 1.
Can you use this one? C1 equal to standard part of x1 divided by a lambda 1? This one, yes?
No, C1 is not related here. It uses already what is above. Yes, so I take this x1.
Yes, x1 equal to x0 minus c0 a lambda
C0
naught.
a lambda naught.
Okay, then a lambda.
Yes, and what I wanted to say, that if you take this, this is not in the set lambda 0. Yes? because to be in the set lambda 0, we have the number a lambda 0, which is there, neither 0 nor infinity. Yeah? So we have to divide on this and see the result. If it is bounded and positive, more than some standard number, then it is in the sum. If it is infinitesimal after we divide it, then we get into other set, lambda 1. Lambda 1 is less than lambda 0. And so we see that if you really take x1 divided by a lambda 0, then the standard part of this is 0, and if you don't write standard part, it is simply infinitesimal. Yeah? So this means that lambda 1 is less than lambda 0. Okay, so now we can proceed the same way. Okay. So, and we write x I plus 1 equals xi minus ci a lambda I. Lambda I plus 1 is lambda of x I plus 1. Ci I plus 1 equals standard part of x I plus y divided by a lambda I plus y. And s I plus y equals s I plus c I a lambda I. And again, so it is for I in n. So you see what happens. We at every time we subtract something which is multiple of this number, which is sort of elemental basis. Subtract something, and this coefficient is standard number. And we see that lambda I plus y is always less than lambda I, by the same reason as I showed there. Yeah? So we go down, down, down. Now, suppose we did it for all I, for all natural I. And what should we do next? Next, we have to go to different paradigm. We have to look at this index I as an ordinal. So what is ordinal? So we can arrange all the sets by their, I would say, the ordinal, so we can, so the integer numbers are form a well-ordered set. Yeah? Now we can extend this well-ordered set, add one new element which is called omega, yes, and then go omega plus 1, omega plus 2, and so on. Then we have 2 omega, then we have n omega, then we have omega times omega, then we have omega to the power omega, and so on and so on. So this way we construct such a generalized sequence of, in fact, all of these elements are sets, because even integer number is also a set in the set theory. So we have a sequence of sets, ordered set of sets. These sets, this order is well ordered, so for any set of these ordinals we can find the minimal element, yeah? And so these ordinals are of two main types. One element is one type are called successive ordinals. So alpha is called successor ordinal. If alpha equals beta plus 1 for some ordinal beta, yeah? And alpha is a limit ordinal if alpha is not successor. Yeah? No, for example, if you write 1, 2, and so on, all the natural numbers, they are ordinals, yes, and each of them is successor, except of one ordinal, and then you write new thing omega, which goes after all these ordinals, and this the omega is a limit ordinal. What next? Next goes omega plus 1, and so on. Omega plus omega. So omega plus omega is another limit ordinal. And so on. So we have here also ordinal omega times omega, omega to the power n, somewhere omega to omega, 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 omega times, and so on. So very soon our imagination fails, so we are talking simply about this omega without any graphical representation. And it turns out that for any set M, there exists ordinal model M such that model M, the set alpha less than model M has the same power as M. No, essentially this is the Zermelo axiom, because if you find such ordinal for set M, then M is into one-to-one correspondence with this sequence of ordinals. This sequence is well ordered, and so we can transfer this well order on M. And I write that model M is called cardinal if model M is the smallest ordinal with the same power as M. No, for example, omega is cardinal because any smaller ordinal is already finite number. Yeah, so it is the smallest infinite cardinal. Omega is the cardinal countable. Countable cardinal. Cardinal the smallest. And okay, and our well ordering of the non-standard numbers is of course made by putting the non-standard real numbers into one-to-one corresponding with its cardinal. Let me write it too. The well ordering of star R is established by putting star R into one-to-one correspondence with its cardinal. Model star. Yeah. No, the cardinals, of course, cardinal for any set exists because any set can be put into correspondence with some ordinal, and then among all the ordinals which have the same power, we find the smallest one. Okay, so why I write all these? Because we stopped our construction of the splitting of non-standard number R into some fixed non-standard number with standard coefficients. We stopped it at when it was done for all finite integer indices, and we stopped at what should be the next. And the next, it is the following thing. So we define the set X Ci lambda I, let than omega. It is the set of all non-standard numbers y in star r such that the above process produces the sequence x 0, the sequence what is it? ci lambda I, the same sequence I in N as for X. So given this sequence, Ci lambda I, so lambda I are the say, sort of numbers of corresponding subset of class of comparable non-standard numbers, Ci corresponding standard coefficients, and consider all the numbers such that we can perform this process with all standard number. So consider all standard numbers such that this process gives exactly this sequence. One moment, let me close the bracket. No, this set is not empty because at least one element is here, because we just finished this process for this element x and have an element of this set. Yes? And now let us define the element A, Ci lambda I is less than omega, is minimum element with respect to our relation in the X Ci lambda I less than omega. Yeah. So we have this set, it is not empty. Take a minimal element with respect to this relation. It exists and is unique. And then we proceed as follows. We write S omega equals A Ci lambda I less than omega. S omega X omega equals X minus S omega. Lambda omega equals lambda of X omega. It is next. C omega, standard part of X omega divided by A lambda omega. Everything is defined. So we found this next element. So we jumped to the first limit ordinal. Now then we proceed with this first limit ordinal, proceed with the further terms. The same way, define x omega plus 1 with next of omega equals x omega minus c omega a lambda of x omega. What else it was? Lambda omega plus 1 is lambda of x omega plus 1. C omega plus 1 equal standard part of x omega plus 1 divided by a omega plus 1. I would say lambda of x omega plus 1. And s omega plus 1 equals s omega plus c omega a lambda omega. And so on. So here we have again the countable number of successor ordinals. And then we reach reach the ordinal omega plus omega. And we write again a c I lambda I less than 2 omega equals minimum in this sense x c I lambda I less than 2 omega. It is all the numbers such that this process which I just performed produces this number, this element Ci and lambda I. Okay, this way we define this element and then go like this, simply replace omega by 2 omega. Yeah. So this way we have we can go from I to I plus 1 for any ordinal I, and if you reach limit ordinal, we can jump to this linear limit ordinal from all the previous ordinals. So we can proceed this way until what? Until what happens? At some moment, what will happen? We will have that the next x is 0. Yeah, and so the process will be over. Yeah, and why this will happen? It will inevitably happen. It will happen by the following reason. It is just counting reason that the number of our steps is not more than the number of elements of the set lambda, because at every step we go down the order of the set lambda capital. Yeah? And the cardinality of the set lambda is not more than cardinality of this whole set star R. Yes? And after we performed the number of, if I would say, so we have a well-ordered set. Yes, a well-ordered set. This well-ordered set is one moment. In short, the number of steps which we perform cannot be more the cardinality of the number of this sequence of steps, or sequence of the x xi cannot be more than the total number of non-standard numbers. Yeah? So if we reach the ordinal such that corresponding cardinality is more, then all the elements are exhausted. Because we go by definition without repetitions. We do not repeat terms. Yeah, so it is the same, I would say, pigeonhole principle. Yes. So this means that after the number of steps not more than cardinality of star R, the process will be finished. Yeah? And so this we have a sequence. We have a sequence of what? A sequence of element lambda I. And I introduced the last term, which is the last today. So the set of lambda I is called spectrum of X. So we have with some freedom in choice, we have defined a new object spectrum of X, and we have this Ci. It is a function on spectrum of X. Spectrum of X. Yeah. So this is what we are working with when we define the asymptotic space of the Lobachevsky plane. So next time we will finish and really see how it is related to this geometry. But it is fun, isn't it? Okay, so let's finish today, and please, so if you have your assignment, please give it to me. If you have not, you can bring it on Friday. Or send it me by email. Just scan and send me.